You know that sound? That horrible, subtle humming sound you can hear across the factory
Oh,
floor?
yeah. The one that means something very expensive just went wrong.
Exactly. It's the sound that tells you that the last 12 hours of precision work, it's about to become a pile of scrap metal.
Hmm. A very expensive pile.
If you work in large-scale manufacturing, especially with those enormous gantry machining centers, you know that hum means x-axis vibration has just wrecked your surface quality.
And it's doing worse than that. It's actively destroying the machine from the inside out.
Well, you sent us a whole stack of sources on this. Articles, maintenance manuals, engineering papers, all about this really frustrating issue.
It's a huge one.
So today, we're doing a deep dive into all that material. We're going to try to solve this critical and very costly problem.
Let's do it.
Our mission for you is pretty simple. We want you to understand the full impact of this vibration, identify the four main culprits behind it, and then lock down the systematic process that experts use to fix it for good. We're giving you the shortcut. Okay, let's unpack this.
I think it's so important to frame this right from the start. We're not just talking about some minor technical glitch.
Right, not something you can just ignore.
No, you can't. When you hear that jitter, it's a sign of a profound systemic failure. You have to look past the ripple on the part and focus on the root cause, the stress, the electronic confusion that is compromising the integrity of your whole system.
Let's start there then. With the immediate consequences, the things that hit the bottom line right now, the first thing you'd notice is just bad parts.
Right. Degraded machining accuracy. You'll see visible ripples, textures, even chatter marks on the surface.
Which means an immediate scrap part.
Instantly. But the truly insidious cost is the mechanical stress. That constant vibration is like taking a tiny hammer to your critical components over and over.
Hammering what, specifically?
The guide rails, the ball screws. These things are designed to last for a certain number of cycles, but when they're perpetually oscillating, their lifespan just plummets
So the wear accelerates.
dramatically. And that leads to expensive, unplanned downtime when something finally gives out. It's death by 1,000 tiny high-frequency blows.
Can you give us a sense of scale here? How bad can this hidden damage really get?
Oh, absolutely. The vibration is the system literally screaming under stress. Remember one case study from your sources that was, well, it was a lesson learned the hard way.
What happened?
A minor, what they thought was a tolerable jitter, was ignored for a few weeks.
Okay.
That constant oscillation from the vibration eventually overheated the servo motor drive.
And it just burned out.
A complete catastrophic motor and drive unit failure. That wasn't just unplanned downtime, that was a full capital expense to replace the whole unit.
Wow. But on the flip side, fixing it must have a pretty big payoff.
An immediate, quantifiable return.
Yeah.
That same study showed that after they resolved that x-axis jitter, the machine's overall accuracy improved by 30%.
30%.
Just by fixing a hum.
30%. You aren't just saving the machine from destroying itself, you're unlocking its actual potential. That's a massive return on investment for anyone listening. Okay, so let's pivot. If ignoring it is so costly, why does a reliable, heavy-duty machine just suddenly start shaking?
It's that delicate dance, like you said, between the heavy iron, the physical structure, and the delayed electronics that control it.
Right. And your sources point to four main culprits, a sort of checklist.
Exactly. And they're usually split between the physical and the digital, so to speak.
We've got the primary causes, which are the most frequent, mechanical wear and servo system instability. And then the secondary causes, which can be trickier to find, electrical interference and just overly aggressive programming.
And we have to start with the most common one because statistically, this is where the problem is going to be.
Mechanical causes.
Mechanical causes. The x-axis on a GMC is huge. It carries a tremendous amount of weight. And all that heavy cycling, day after day, means the guide rails and ball screws just wear down. It's inevitable.
And that wear creates what? Tiny gaps?
Exactly.
Yeah.
Tiny gaps are what we'd call looseness. Technically, it's mechanical play. Think of it like a loose steering wheel in a car.
Okay, I see.
When the controller says, stop right here, or reverse smoothly, that tiny bit of play turns directly into the jitter you see and hear. The machine is hunting for a tight spot that just isn't there anymore.
That makes perfect sense. But what if the hardware feels solid? If everything is tight, then we have to look past the muscle and check the brain.
Precisely. The servo system, that's the control system driving the motor. And this is where we get into some jargon, but it's important. The servo parameters.
The gain settings, right. For listeners who haven't tinkered with these, how should we think about gain?
It's like the servo motor's level of anxiety. or its responsiveness. If the gain is set too high, the motor is hyper-responsive.
Yeah.
It overshoots its target, realizes its mistake, tries to correct, overshoots again.
And it just gets into a fight with itself.
A fight with itself. That's a perfect way to put it. And that fight is the high-frequency buzz you hear. If the gain is too low, it's sluggish and lazy, and it won't hold its position accurately. You have to find that sweet spot.
A motor fighting itself is a great image.
Yeah.
Now, what about those trickier secondary causes? The electrical issues?
I call this the ghost in the machine. About 15% of cases are caused by electrical interference.
How?
Poorly shielded cables.
Yeah.
They get old, or maybe they weren't installed right, and they start acting like antennas. So they pick up all this stray electrical noise from power lines, or maybe the welder next door fires up.
And that noise gets into the control signal.
It corrupts the signal. The control system gets these erratic, flawed commands and passes them to the motor. The result is this spurious vibration that's incredibly difficult to trace.
And that leaves us with the last one, the operational cause. You've checked the hardware, the servo is tuned, but the machine still shakes.
That's right. The program itself is the problem. This is usually the easiest one to fix.
Just pushing the machine too hard.
Exactly. Pushing it beyond its physical limits with excessive feed rates or acceleration curves it wasn't built for. And what's fascinating here is the vibration isn't from a component failure. It's because the command is asking the impossible of the machine's sheer mass and inertia.
So we know the damage, we know the four main causes. The real challenge is figuring out which one it is without tearing the whole machine apart.
Yes. Guesswork is expensive.
Yeah.
You need a systematic blueprint,
A diagnostic process.
a strict order of operations. You have to isolate the variable, and you always start with the simplest, most likely cause.
Mechanical parts.
Step 1, manual inspection. Power must be completely off. You manually check the X-axis guide rails, the ball screws, the bearings. You literally try to rock the axis by hand and feel for any play.
And you mentioned an incredible story from the sources about this manual check.
I did. The source material details this case, where the entire problem, all the scrapped parts, all the downtime, it boiled down to a 0.02 millimeter gap.
0.02 millimeters. That's what, less than a human hair?
Less than the width of a human hair. And all that noise, all that scrap, came from something you couldn't even see with the naked eye.
Unbelievable.
But that's how precise these systems are. That tiny amount of mechanical play, multiplied by the forces involved, it becomes a major vibration. So the mechanics feel tight, then we power up.
Okay, power's on. What's the next tool?
Step 2 is the vibration analyzer. This is your truth teller. The frequency spectrum tells you the story.
How so?
A low-frequency thumping, maybe under 100 hertz, that almost always points right back to those heavy mechanical issues. A bad bearing, worn rails, that ball screw looseness.
Okay.
But if you see a higher frequency, sustained buzzing or singing, often above 400 hertz, that strongly suggests servo instability, the motor fighting itself,
Yeah.
or maybe that electrical interference.
So the analyzer immediately splits the search. Low frequency, grab a wrench. High frequency, grab an oscilloscope.
Exactly. But before the scope, there's an intermediate step. Step 3 is using the machine's own CNC system monitoring.
The built-in diagnostics.
Right. You can actually watch the motor's current load on the screen. If you see the current spiking rhythmically, even when the axis is moving slow or just holding still,
It means the motor is working way too hard.
it's drawing excess power just to maintain its position. That's a huge red flag for a servo drive or a motor issue.
Okay, so we've checked the mechanics, we've checked the current. If that high-frequency buzz is still there, we have to look for that digital boast,
Now we get to the really interesting part.
the most powerful tool.
Step 4 is the high-precision oscilloscope check. This is the final word on electrical integrity. You hook up the scope and look directly at the encoder feedback data stream,
And the encoder is what tells the servo exactly where the axis is, right?
down to the micron. It should be sending a clean, perfect square wave signal back to the drive.
And if it's not a clean signal, what does that look like?
If it's corrupted by noise, that clean square wave looks messy. It gets jittery. You see noise spikes, distortion on the edges. If the machine can't reliably read its own position, it can't stop shaking. It's like trying to drive in the dark with a flickering flashlight.
You just can't hold a straight line. That systematic process is priceless. So once we've found the root cause, we need a permanent fix. No more Band-Aids, like just slowing the machine down.
No, because that just kills your productivity. The fix has to be targeted. If our analysis pointed to low-frequency noise and we found play, we need mechanical fixes.
Like replacing worn bearings.
Or, critically, adjusting the preload mechanism on the ball screw to eliminate those tiny gaps we talked about.
What does adjusting the preload actually do?
It's a procedure where you slightly compress the components inside the ball screw to remove all that internal slack. You're taking up that 0.02 millimeter gap. And of course, proper lubrication is huge. Reducing friction smooths everything out.
Okay, and for the 20% of problems that are servo-related,
That's when you go into the drive controller and you start tuning those servo parameters, carefully adjusting the position and speed loop gains to find that sweet spot again.
the goal is to damp the jitter.
Stop the motor from overreacting. Let it settle precisely on its target without that overshoot and oscillation. It's an art form, but modern software helps a lot.
What's the biggest mistake people make when they try to adjust game for the first time?
Overcorrection. They hear the buzz, they panic, and they just crank the gain way down. The shaking stops, but now their machine is slow and sloppy, completely incapable of precision work.
Or they go the other way.
Or worse, they crank it too high thinking faster is better, and they burn out the drive or motor by forcing it into a constant state of panic. It takes incremental, measured changes.
And finally, silencing that ghost in the machine, the 15% electrical interference problem.
If the oscilloscope showed a messy signal, the fix is structural. It's all about shielding. Installing proper anti-interference filters, making sure signal cables are shielded and routed away from power lines,
And grounding, I assume.
and crucially, ensuring a solid, dedicated earth ground. Poor grounding is a non-negotiable error. It's an open invitation for ghost vibrations.
And we can't forget the easiest one, the 5% caused by the program.
Exactly. Reviewing the CAM program, just making sure you aren't commanding these sudden, violent acceleration changes can often prevent the vibration from ever starting. It's a quick win.
All right, now for the ultimate shortcut. This is where your source is really delivered. We have data from 50 different CNC gantry machining centers, and it gives a statistical breakdown of where you should be looking first.
This is the key takeaway, really. The statistics are crystal clear, and they match what people see in the field. The overwhelming majority, 60% of these X-axis vibration issues are caused by mechanical wear.
60%. So that validates the whole process. Step 1, check the mechanics manually is the most important thing you can do.
It tells you that 6 out of 10 times the solution is mechanical. Worn rails, loose screws, bad bearings. The heavy iron takes the abuse.
What's the next biggest chunk?
20% is attributed to servo system instability. This auto happens after a machine is moved or a new part is installed, and it just needs to be retuned.
Wait, 20% is still huge. So you're saying 1 in 5 times, if I hear that high-pitched buzz, I might just need a technician with a laptop, not a whole new motor.
Precisely. And that's the difference between a few hours of skilled labor and thousands of dollars in hardware with a 6-week lead time.
And the rest.
Then you have that trickier category, electrical interference at 15%, the ghost. And finally, the easiest fix, that last 5%, is just improper processing parameters.
So if we connect this to the bigger picture,
The data tells you to start with a wrench. The odds are overwhelmingly in favor of it being a physical looseness issue. Start there, then move to the electronics.
so what does this all mean? We've learned X-axis vibration is primarily a mechanical problem at 60%, followed by servo tuning at 20%. And the path to fixing it is systematic. First, check it by hand, then listen to the frequency, then monitor the current, and finally, check for bad signals.
And then you apply the targeted fix. Replacement, tuning, or shielding.
That systematic, data-driven approach is the only way to avoid that costly guesswork that just cripples production.
It is.
It truly is. And as a final thought for you to chew on, since the vast majority of these failures, that 60%, are caused by the physical wear and tear of the heavy iron, and 20% are from electronic tuning, consider the continuous challenge here. We are constantly asking these ultra-precise, super responsive electronics to compensate for the inevitable physical breakdown of the giant mechanical structure they control.
It's a constant battle.
It is that persistent tension, the need for digital control to constantly fight and compensate for physical reality. That's the core engineering challenge of the modern factory, and it's something worth exploring further.